Okay, hello everyone. This is a video on inscribed angles and their arcs. So if you need to pause the screen, here's a couple of definitions on there for you if you don't have these notes provided by your teacher. Quickly, there's an example picture here of what an inscribed angle is. I always like to think about inscribed angles sounding like inside. Inscribed literally means drawn inside of the circle. So inscribed sounds like inside, so I always think the angle's inside. Now, what's different about an inscribed angle than a central angle? Remember, a central angle is an angle located at the center. So it's an angle that looks more like this, where the vertex is at the center, and then that angle right there was equal to this arc right here. But that's not what we're dealing with an inscribed angle. What we're working with here is the vertex is actually on the circle. So you could see that the angle has almost been stretched further back. Like if you ever held a rubber band between your fingers and you stretched it back like you were going to shoot something or shoot it at somebody, you stretch that further back. And that means that that angle, when you stretch it back, is actually getting smaller. So we're no longer having an equivalent relationship between an angle and an arc anymore. But if you look slightly below that, you'll see that an inscribed angle is half of its intercepted arc. Remember, intercepted arc is the portion of the circle that's in between the sides of the angle. So for instance, this is the inscribed arc right there. So that portion of the arc, or of the circle rather, is the intercepted arc that we're talking about that goes with the inscribed angle. So if I told you that the measure of this angle here was, say, 80 degrees, the arc is twice as big, so 160 degrees. If I go the other direction and I told you that the arc was 200 degrees, then this angle would be 100 degrees. All right, so that's how that's going to work. The arc is twice as big as the inscribed angle. The inscribed angle is half the measure of the intercepted arc. So make sure you make that connection. Inscribed is inside, the vertex is on the circle, and the measure of the inscribed angle is half of the intercepted arc. Let's slide over and do an example to really drive this point home. All right, so here we go. We are going to solve for x and y. All right, so we've got two different inscribed angles here. You'll see we have angle ADB, and their inscribed arc is arc AB. And then we have inscribed angle FBD, and its its intercepted arc is FD right there. So I'm just going to start to solve for x. So 70 is the inscribed angle. And remember that the arc, 2x plus 18, is twice as big as the inscribed angle. So that's the setup there that we're going to use to solve for x. So that means 2x plus 18 is equal to 140. Subtract 18 from both sides. 2x is equal to 122. Divide both sides by 2. X is equal to 61. So x is 61. Now we're going to solve for y. Now notice that 56 is the arc, and it's twice as big as the angle. And in this case, the angle is the 4y. So go ahead and multiply by 2, or you can divide by 2 from the beginning. It's really up to you how you like to do it. I'm just going to go ahead and multiply by the 2 there and distribute, and I get 8y. Now I'm going to divide both sides by 8, and that means that y is 7. So here is my x and my y value, and all they asked me to do was solve, so I don't need to plug that back in and find any angle measures, but if they wanted you to, they would ask. So that's how we're going to use this idea of an inscribed angle being half of its intercepted arc measure. All right, here's a couple other details with an inscribed angle. Right here talks about if you have two inscribed angles that intercept the same arc, they are going to be congruent. Now, I think that might make sense. A lot of you would have figured that out on your own, but just to make it clear visually, angle A sorry, BAD here, just to be real specific. I'm talking about this angle right here. Angle BAD, that's an inscribed angle, and it goes with that arc BD, that's 100 degrees. And then angle BCD, which is this angle right here, that also goes with that arc BD. So because they both have the same intercepted arc, they're going to both be half of the same number. Well, 100 divided by 2 is 50. So both of those angles end up being 50 degrees, and thus they are congruent. So if two inscribed angles share the same intercepted arc, they are congruent. All right, now we have this next idea right here that might be a little bit confusing, but I think I'm going to try to do my best to make it as easy to follow as possible. If you have an inscribed polygon, remember we used inscribed earlier like inside. So this thing is drawn inside the circle. Now, it's any sort of polygon, but we're going to be really specific about it being a quadrilateral. So we got an inscribed quadrilateral. So if you have an inscribed quadrilateral, and it doesn't have to be any kind of specific quadrilateral, it doesn't have to be a rectangle, it doesn't have to even be a parallelogram, it could just be any run-of-the-mill four-sided polygon. If you get a quadrilateral in there, then a really nice relationship occurs. The opposite angles are supplementary. That means that the opposite angles are going to add up to 180 degrees. Now, you're thinking maybe, why is that? Well, if you look at this angle O right here, its intercepted arc is all of this. That's its intercepted arc. And if you look at the angle M, which is across from O, this angle right here, its intercepted arc is all of that right there. Well, that's the whole circle. And the whole circle, if you add all those arcs together, that's 360 degrees. And we know that inscribed angles are half of their intercepted arcs. So 360 divided by 2 is 180 degrees. So I don't necessarily know what the measure of angle O is or the measure of angle M is, but I do know that those two angles together are going to add up to 180, because those two angles sum is going to be half of the whole circle, because that's what their arcs make. So the idea that opposite angles add up to 180 is super important. So let's go ahead and write that down on your notes. If you want to take a second to do this, I'll write this down for you so you know what to write. So inscribed quadrilaterals have supplementary opposite angles. That means the measure of angle O plus the measure of angle M equals 180, and the measure of angle L plus the measure of angle N also equals 180 degrees. So if you want to copy that down, pause your screen real quick, you can do that. But make sure you understand that you got a quadrilateral inside that circle. Opposite angles add up to 180 no matter what type of quadrilateral it is. All right, we got an example right here below, and I'll work through that with you as we finish out the video. Okay, so what we've got here is the measure of angle I is 95, so that's this angle here. Okay, then the measure of angle K is 85. And the directions are, if the polygon is inscribed, then its opposite angles are supplementary. So this is just basically making sure that 95 plus 85 is equal to 180 degrees. Is that a true statement? Yes, it is. 95 plus 85 is 180 degrees. So that checks out. That works. That's what's supposed to be happening. If angle J was 107, then that angle across from it is supposed to be 73. Well, let's do a real quick check. 180 minus 107 is 73 degrees, and that's what this is supposed to be. So these are one more way to show you that the opposite angles of a quadrilateral are supplementary. They add up to 180. So when you see any quadrilateral inside of a circle, those opposite angles add up to 180 degrees. Okay, good luck. Thanks for listening.